Thanks a lot for the invitation to speak here. It's a pleasure and an honor to start the fall season of the seminar. So this is a talk about joint work with Simone Cecchini and Georg Frenck on scalar curvature with singularities. So the general theme is the general theme I want to report on is Riemannian manifolds with metric singularities, and I want to emphasize sort of the part that this is about smooth manifolds with Riemannian metrics where the singularities are only in the metric. And what kind of singularities are we looking at? So we're looking at metrics which are quite wild in a certain sense. So they are L infinity. What does L infinity mean precisely here? So this is sort of from the sort of type of object like a Riemannian metric. So it's a symmetric 2 tensor, but it's a priori only measurable. But you're going to assume that it's bounded above and below by a smooth metric. So let me just write this in this way. So this sort of means there exist smooth metrics let's say G0 and G1, such that the metric you're looking at is bounded below and above by some smooth metrics. And I'm gonna write just for short G in L infinity to mean precisely this. So if that's the first condition, and that alone I think is like too wild, so that would not be very interesting. But there's sort of an additional condition, namely that it's smooth outside a sufficiently small singular set. I'm going to specify shortly what sufficiently small is supposed to mean. And in terms of notation, I'm going to write G is in C infinity log of M minus S for short. And then the goal is, in a sense, that under such assumptions, study the property of a lower scalar curvature bound. And for such a metric, you can just naively sort of say, okay, a lower scalar curvature bound should be satisfied if it happens on the smooth part. So where you can just define it in the usual way pointwise and then impose a lower bound there. And this is in a sense motivated by the following result, which in a sense started this story to some extent, which is due to Chao Li and Christos Mantoulides. I think it was published in 2019, it's probably a bit older already. And it states the following. So it's about three manifolds, closed three manifolds. And you assume that this does not admit a PSC metric, a positive scalar curvature metric. That I mean in the smooth sense. So this is a manifold like the 3 torus, which does not support any metric of positive scalar curvature. And then the question is, in a sense, are there metrics which are in a sense a little bit weaker, which are sort of this type, but then would admit a metric of positive scalar curvature? And the situation that's going to be looked at here is where we look at a finite subset of the manifold, and then we look at an L infinity metric, which, however, is smooth outside this finite set of points. So it's smooth almost everywhere except for a finite set of points. And we're going to assume that the scalar curvature is non-negative outside that finite set of points. So let's say we have maybe a torus, and then we have some finite set of points where we have singularities in that sense, but otherwise we're smooth. And the theorem tells us that in that situation, the metric is already flat on M minus S. And that is sort of in the same spirit as the fact that we know for a long time that any metric of non-negative scalar curvature, which is smooth and exists on the torus, has already to be flat. And in that case, one knows actually a little bit more. So one can say that in such a situation, it extends smoothly to M after possibly adjusting the smooth atlas of M.
May I ask a question?
Sure.
Because of course, in dimension 2, it is not true, right? So so it looks counterintuitive slightly even in dimension 3 because it's not true in dimension 2, right?
Yeah, I think it
Immediately
should
you
not be
look at
true
this
in.
example, I see it's not, so I'm trying to make counter example. If it's around the circle already, you cannot do it, right?
Right. I think in dimension 2 it should not be true. Yeah.
Yeah.
This kind of statement where you have a
So it's specifically three-dimensional, okay. And
yeah.
it's
So
and it's essential that it's really topology is usual. You cannot say we have manifold with singularities, but you have to specify topology saying it's really a manifold, I guess, right?
yeah. So we're looking at manifolds. Yeah.
No, but I'm
So
saying
we
that okay, my first question is how essential was that the singularity is still standard topology, but probably what essential that your singularity, your base, is, if it's conical, yeah? So the base of the cone must have a certain topology spherical in the dimensional case. I'm just thinking what is the picture.
right. I think the
What picture to make in mind? Yeah, I mean just
yeah. So I think we want to assume that it topologically closes up to a manifold. So the link should be a sphere,
no,
not
not only topologically, but also smoothly.
and also smoothly. Yeah, also in a sort of in a smooth manifold
Tend
sense.
to smooth manifold in a certain smooth way. Okay, but
Right.
because natural questions is for isolated singularities, you don't assume anything about the singularity, right? You just smooth outside in singularity, and then you have to describe it in terms of the cone, not in terms of background. This I feel slightly uncomfortable when you force background something. You see, it's not mathematically, geometrically, it's unusual. In physics, they allow it. They have background and then perturb. And here you force your background. Okay. But I'm
Yeah,
saying,
I'm assuming a smooth
what
background
would be the
manifold,
correct
but I'm
theorem
not.
here? In
Yeah.
this in this theorem, what would be correct statement? It's not that it come from smooth manifold, but something about behavior of this metric. No, you see, this metric must encode the properties, not your a priori assumption. See my objection to that, yeah? You have to say in terms of metric of outside of this point, you have to say what condition is, not saying that plus extra structure, you see? Because the structure you have smooth manifold, not
Right.
complete in some metric. And then you have to say what you add about the singularity. Then say, oh, let's assume there is coordinate system. This is certainly a very unpleasant condition.
Yeah. But I think the setup is really it's just a smooth manifold, so there's no metric on it. So that's sort of some intrinsic object, and
No,
then
no,
we're
no, no,
looking
no,
at
no. We want to
the
justify a definition. Say geometrically, it's wrong definition. Period. I understand what we say. It's easier for you to say.
yeah.
I think the right condition should be you have a smooth manifold, non-complete metric with certain property in this non-completeness, and then you have to describe these properties in terms of extrinsic metric, right? Because you throw in structure which is not naturally there, right? This is what I'm saying. It seems to be a wrong condition. The right statement naturally maybe I'm wrong, should be the way I said. You have smooth, non-complete manifold, and something is true without saying there is extra structure, which completely invisible in terms of this geometry. See, maybe I'm completely wrong. Yeah, but my question, even for this theorem, what would be the correct statement? And
I
the
think
correct.
we're gonna when we go on, we're gonna see that there is in fact
So
I think
is it
some
true,
some
for example, for this theorem, if the only thing you know, the topology is right, that at every end topology is spherical. That's it. You don't say there is smooth background. Just say topology is right around singularities.
I
If
think
this theorem remains true.
I think for that particular, I imagine something like this should be true. Yeah, I think
Okay.
what you kind of I think for that what's in the background of this is that the underlying manifold, like the one you get when you remove the point, so you forget about the extra structure, that this does not admit a complete metric of positive scalar curvature. If you have that condition, I think then you will get something like that. That's true. Yeah, but sort of What this is
wait. If it had conical if it have conical or something else, yeah, it's point singularity. So this might be true much more general. Because he's here spherical, yes. This what you said is not right condition. Condition is if you need any condition at all here. You have a manifold and there is singularity, say conical. Imagine they're conical. Yeah.
I mean, we're going to see that maybe let's go on a little bit. I'm going to see sort of different kinds of examples and counterexamples, and then maybe it also becomes clear what the or we're going to like find maybe a better condition.
So no, but this is like a financial question. What one singularity and what condition? Yeah, what you can say. But here probably in dimension 3, I don't see any condition needed. Is there any condition? Just to have
no, I mean there's no. I mean
it's just singularities.
It's just this Ln.
If you just say conical, do you need any condition? No, approximately conical. Do you need any condition?
Do you mean on the metric or the?
Nothing. This manifold point to scalar curvature which has conical singularity on the torus. Is it possible or not?
I mean, conical would be even
approximately conical or something. Yeah.
Yeah, I mean, this is a special case of this. I mean, this is more general than conical. I mean,
I'm asking my question: is it possible or not?
No, it is not possible. I mean, this is the conical singularity would be okay, in this
condition. Its completion is 1 point. Yes, singularity completion is 1 point. 1 point singularity without saying anything about what. Is it possible? I just want to see what is the true theorem. Do we need it or not?
Do you mean the infinity condition?
Is it actual theorem or just technical condition? Is it a true theorem or just technical theorem? See, if it's ultimate condition understood or just technical, this is the fact sounds natural. It's not.
I mean, I think this L infinity condition, this is quite general. I mean, it's certainly includes.
No. The L infinity depends on background. L infinity needs some background metric. Background structures.
Maybe we could see what the examples are and what he wants to present, and we can figure out the answer.
No, but my question is, in this three-dimensional,
we understand your question.
Do you need any condition? Yes or no? I need yes or no answer. The torus minus there is a manifold which is admits.
I think if you do things like so. Let's see. I think negative mass Schwarzschild metrics, if you complete them with a torical end at infinity, you might you will get examples where you have non-flat metrics on the torus of some singularity which violate this L infinity condition.
So it's possible. Okay.
I think that's that. Now I think I understand the question. So I think that's.
Okay. So we need some example, counterexample. Okay.
Yeah, I think taking sort of at the interior the sort of the singular.
Because see, if you say just
singular boundary of a negative mass Schwarzschild, collapse that to a point that at infinity you deform it so that you can complete it with a torus. I think that's gonna be a counterexample if you drop that condition.
Okay.
Yeah. Okay. So now that comes sort of that like motivates or what comes now motivated that theorem. Either way, there's a conjecture which is attributed to Schoen, which sort of generalizes that theorem or like proposes a way of generalizing that theorem. And the proposal is that if you consider a closed manifold again, which does not admit a smooth positive scalar curvature metric. Again, like the torus, but also maybe a K3 surface, all the examples of that kind that we know. And then we consider some submanifold. Maybe it doesn't have to be a submanifold per se, but let's take a submanifold, which is going to stand in as the singular set for metrics that we're going to look at. And the condition now is that the codimension of that subset should be at least 3. So in the case of 3-dimensional ambient manifolds, this means precisely that the single set is 0-dimensional, so we have points. And this also sort of excludes then now looking at 2-dimensional examples. And then the statement of this conjecture is the following. So I'm going to state it in a, I guess, more verbose way than necessary, but I want to sort of tease out the different aspects of that conjecture. And there's sort of one obstruction part of this, which says that there exists no L infinity metric which is smooth outside this singular set, which has positive scalar curvature. Now, this is sort of the obstruction part. So the idea is, okay, there is no smooth positive scalar curvature metric, then there should also not exist a singular positive scalar curvature metric. And then corresponding to such an obstruction statement, there's usually a rigidity statement, which is in the same vein as in the classical sense that if we have a manifold which does not support positive scalar curvature, then any non-negative scalar curvature metric must be Ricci flat. And that's sort of the rigidity part here as well. So if you have now such an L infinity metric, which is smooth outside the singular set, has non-negative scalar curvature, then it is Ricci flat on the complement. And then sort of as an additional, maybe more ambitious statement would be that in that case, it actually extends smoothly to all of them. In the same sense as above that we might have to possibly adjust, but I'll say more about that. But before saying sort of more about that, let me quickly run through what we know so far about this conjecture. So the first is the three-dimensional case. This was the theorem that I started with. Now this is known. If the dimension is 4 and M is enlargeable, so for instance the torus, then the obstruction and rigidity part of this conjecture, so sort of up to here, is also known to work of Dimitri Katsaros. I think it was published in 2024, but also has been out for quite some time. And now in our work, which I'm going to present, we also have results, and I'm going to want to briefly mention them without going into too much detail. So what we showed is that the conjecture holds under a certain index theoretic condition. And I guess for us, for today, I only want to point out that this is, for instance, implied by enlargeability. So enlargeable spin manifolds are included in the result that we have. And we have a result for point singularities. So we have an arbitrarily dimensional spin manifold, which satisfies a certain condition, namely that the so-called Rosenberg index really comes from the fundamental group, so it does not lie in the image of the trivial group, which is indicated by that notation, which happens in many cases, and in particular happens in those cases where the non-triviality or the non-existence of positive scalar curvature is due to some sort of largeness property like enlargeability. So enlargeable spin.
Here is a point singularity. In this example, it's high dimensional, but you speak about point singularity.
So
yeah?
yes, I speak about high dimensional manifolds.
This conjecture shown is very unlikely for high dimensions, of course. Yeah, if you go dimension 7 or 8, it's probably not true. Yeah.
That's right. And
obvious potential counterexamples, probably counterexamples.
Yeah, we're gonna see them soon. So
you take a torus, throw away, so you need dimension more than 6 or something. Yeah.
Yeah. So for the torus, it's sort of okay. So if you have point singularities for the torus, then this is included here. And again, we have the sort of abstraction and rigidity part here. And maybe also let me mention that recently afterwards, we also there's a nice paper by Wang and Ji, where there's a similar result for it's related to the torus or even more general enlargeable manifolds, where the subset is even allowed to be more general than points. And there's a condition that you have a non-zero degree map to the torus or enlargeable manifold. And there's also a fundamental group condition, namely that this map induces the zero map on the fundamental group of the singular set. And I want to sort of this is sort of what's known in the positive direction on this conjecture, and what in particular one sees here is that this sort of tends to happen when the fundamental group plays a non-trivial role in the non-existence of positive scalar curvature. Now, like
but excuse me again,
adaptability.
that's the reason kind of I'm worried about the following thing. So take high-dimensional torus and take skeleton of sufficiently high dimensions, such that in this complement, as you know, there is a metric of complete metric of positive scalar curvature.
Mhm.
Can you this completeness turn into your kind of metric? You see, because we see
Yeah, I
you
think
have large
that
dimension, and lots of metric there is complete outside of the skeleton. So what is?
I don't know precisely about the torus in that case. So this is I
But
think
this is suspicious case where things
it
might go wrong.
is indeed a suspicious case, but there are sort of simpler, even more suspicious cases which we're going to see. So now let me go into the sort of phenomena which show that there are some issues with this conjecture. So the simplest case where you can see this, or sort of the simplest case where you already see problems, is if you think really closely about this extension question. Yeah? And so if you think about the following, so let me recall the so-called Alexander trick. Yeah? You take a diffeomorphism of the sphere of sort of one dimension less, then you can always extend that to a homeomorphism of the disk, just by coning or just radial extension, just by this formula if you want. And so this actually works for any homeomorphism, turns a homeomorphism of the sphere to a homeomorphism of the disk. And if you start with a diffeomorphism, however, then it will be a diffeomorphism except at the origin. So this construction is obviously smooth except at the origin where it is not, and in general it will not be. So it's only a homeomorphism, but it is the diffeomorphism, or it is smooth on the disk minus a point. And this sort of interacts with this sort of question in the following way. Now you can, let's say you take any Riemannian metric on the disk, any smooth Riemannian metric, and then you can just do something very simple. You can just pull back with this Alexander homeomorphism. I mean, this only makes sense outside the origin where this is smooth. But it's going to just give you, this is sort of easy to check, it is going to give you an L-infinity metric. So it's going to give you an L-infinity metric on the disk, which has a single point singularity at the origin. Okay, so this is already sort of one construction which allows you to construct L-infinity metrics, which in general will not extend to a smooth metric. If you basically, whenever you take some random diffeomorphism, this will not extend smoothly to the Alexander point, to the origin. And now you can play games like you take a diffeomorphism, which is sort of random, but it is, however, isotopic to the identity. And then you can take that on your disk here, and if you know that this is isotopic to the identity, you can sort of homotop it, or like interpolate it to the identity diffeomorphism outside a slightly larger disk, and that way you get a compactly supported diffeomorphism on a disk, which you now can glue into any manifold you want, pull back any metric you want, and you get a non-trivial metric, which is L infinity, has a point singularity, but with sort of for silly reasons does not extend smoothly to the point you had removed. And you can in particular also do this on the 3 torus if you want. And this is why you have to, when you talk about this extension problem, you always have to say some caveat that you might have to change the smooth atlas near the singularity if you want this to be true at all. So this sort of is a local problem, but it automatically also leads to global problems. And this is because now let's start to look at sort of interesting global examples. And the first type of interesting global examples would be homotopy spheres, or let's say exotic spheres. That means manifolds, smooth manifolds, which are homeomorphic, but not necessarily diffeomorphic to the standard sphere. Because in that case, let's say, at least, let's start with dimension 6. Then we know that we can always write this as basically by an application of the H-Gabordesen theorem, can always write this as gluing 2 disks together along a diffeomorphism of the boundary. So where F would be a self-diffeomorphism of the sphere. And then if you have that, the way you can explicitly write down a homeomorphism to the standard sphere would just be using this Alexander trick. Yeah, so you can now on 1/2 of this sort of fake sphere, where you glued together 2 hemispheres along a non-trivial diffeomorphism, and then you write down a map to the standard sphere by taking the identity on one hemisphere and taking the Alexander map on the other half. Yeah, so you get a map F to the standard sphere. You can write it as gluing together 2 disks along the identity, and it would just be the map, which say on 1/2 is the identity, on the other half is this Alexander trick map. And once you've realized that, you can pull back the standard round metric along this map to the exotic sphere, and you get the following result, which is the following, that any exotic sphere, I'm now writing in starting from dimension 7. This is just because that's where the first examples exist, which really are homeomorphic to the sphere, but not diffeomorphic. No? But of course, this is true for any standard sphere as well. So any exotic sphere admits an L infinity metric, which is smooth away from a single point, and a homeomorphism to the standard sphere, which is a diffeomorphism outside this point, and which pulls back the round metric to the given metric on the complement of that point. And it follows from this construction. And now, why is that a problem? So this is a problem because there are exotic spheres which do not support metrics of positive scalar curvature. And this means we have immediately sort of concrete counterexamples to the strongest state version of this conjecture, in a sense, because already the obstruction statement is false, because these manifolds do not support smooth metrics of positive scalar curvature, but they have an L infinity metric, which is smooth away from a single point, which is there isometric to the standard round metric, and therefore has scalar curvature equal to n times n minus 1 there. And in fact, this is the whole manifold is sort of outside that point, isometric to the round sphere. So and I think I think the comments from the beginning, Misha, they're sort of in a sense right at this point, because they sort of show that this sort of L infinity metric does not really see the smooth structure of the background manifold, because it sort of doesn't see the smooth structure. The global smooth structure is somehow stored only, or can only be remembered when you sort of remember how you glue back in that missing point, and the L infinity metric cannot see this, and sort of this is sort of an immediate mismatch that produces sort of counterexamples to this statement. Okay, let me also mention a recent theorem which sort of goes into a very similar direction, which is due to Chu, Li, and Chu, which is essentially a version of Yarul's theorem for L infinity metrics of point singularity. So this is Yarul. Let me read the conditions. So you start with a closed spin manifold, and you start with an L infinity metric, which is smooth outside a finite set of points. Yeah, and you assume that the scalar curvature is bounded below by n times n minus 1 on this on the complement of this finite set of points. And then you have the sort of Yarul hypothesis. You get a Lipschitz map from M to the standard sphere, which is smooth and area non-increasing on the complement of this finite set of points where the metric is smooth as well. And then the conclusion is the Yarul conclusion, namely that F is an isometry, but here one has to the statement is sort of a bit subtle. It's only a distance isometry, and the pullback of the round metric is equal to the given metric on the complement of this finite set of points, meaning there it is a Riemannian isometry. But it is not necessarily a global Riemannian isometry, because then it would have to be a diffeomorphism. The fact that this part of the statement here does not include that conclusion is actually necessary, and these sort of examples show that. So this is, again, we see here we actually have exotic spheres where we cannot expect that this map will be a diffeomorphism. So this sort of even in these cases where sort of there are exotic spheres which do not support positive scalar curvature, there are others which do, even though they're exotic. And for those still the conclusion here cannot be made better. So you cannot get more than this, because then you would get a diffeomorphism to the standard sphere, which does not exist. Okay, and let me mention sort of one more idea, which is now, let's say, okay, so this obstruction part, because of these smooth structure problems, just is not true here. Another question would be, can the extension part sort of alone be true in a certain sense? Let's say on the torus, where you maybe have stronger reasons which are independent of the smooth structure for the non-existence of a positive scalar curvature metric. And here you can just do a very similar construction. So you start with your exotic sphere. So you start with your exotic sphere, which you get by gluing along a diffeomorphism on the boundary. And then what you do is, instead of gluing that into another hemisphere, you can glue that just into a torus, where you sort of remove a disk. And if you follow that idea, you get smooth manifolds, which are obtained from taking a connected sum of the torus with an exotic sphere. And then by sort of a similar idea as before, pulling back a standard metric, you will get a L infinity metric on this exotic torus, which is smooth and flat away from a single point. And that's sort of okay, so that's fine. Why this exists, but this exotic torus has sort of an interesting property, namely it itself does not admit any smooth metric, even of non-negative scalar curvature. So this exotic tori in comparison to standard tori, they are not they don't have zero Yamabe invariant. They're actually Yamabe negative, so they don't admit any Ricci flat metrics either. And so this is sort of a strong counterpoint to the to sort of any sort of global extension result, even in a sense that if you're sort of only change the smooth atlas locally without changing the global structure, you cannot do it. Because if you were to be able to extend this flat metric to the interior here, you would have to really globally change the smooth structure to the standard torus. Okay, so this was actually the first part that I wanted to explain. And so far, it looks like that this conjecture has problems, but these problems are, in a sense, due to the fact that I can play some tricks with the smooth structure, and the L infinity metric, in a sense, does not see that. And we're going to see later, after the break, that the problem effect goes a little bit further, but let me maybe stop now and ask if anyone has any questions in the meantime.
So in your last theorem, can you maybe say again, I think it's sort of obvious, but I don't see it right now, that you do not have a metric of positive scalar curvature away from the point P. I mean, you say you have a flat metric, right?
Yeah, it's a flat metric, yeah. Yeah, so there does not exist a positive scalar curvature metric. So if you want to have an L infinity metric, which is a positive scalar curvature outside that point, that does not exist, because that's in a sense included by these results on enlargeable manifolds that I mentioned in the beginning. So that
I see. Okay.
So you cannot push it up towards positive. This only shows that the extension part already has global problems. Yeah, but even though in that case the obstruction part is okay. Okay, so how was your plan for these sort of intermediate breaks? How long should they be, or is it up to me?
Up to you, of course. I mean, it depends on the interest of the audience.
Yeah. Okay, so it seems like there are no more further questions. Maybe I'll.
Yeah, I mean, you can continue. I mean, we've already had some discussion, and that's the main point, that you have some interaction of the audience with the speaker. And that is the case, obviously.
All right, very good. So, so then let me maybe continue. As I said, what I've shown you so far is that you can sort of change the smooth structure with a diffeomorphism, and then suddenly you run into a problem, and you see that sort of there are some issues which from this conjecture which just come from the fact that whether or not you admit positive scalar curvature or non-negative scalar curvature, this is something which actually depends on the smooth structure. And this L infinity metrics, they don't see how the manifold closes up when you add in the point, and you have sort of different possibilities here in the smooth atlas to get a global manifold. And in that sense, sort of you have a sort of an explicit and sort of straightforward problem once you've noticed that. But what I want to say next is that there are, in fact, more counterexamples. So the issue that we have here is, in a sense, not just a smooth structure. So you will have examples where no matter what smooth structure we have, the underlying manifold just does not support positive scalar curvature, and still we can do a construction in a similar spirit. And let me state this as a theorem, and this is sort of actually our, I would say, main theorem, which says that for any dimension starting from 8, there exists a closed smooth manifold without a smooth positive scalar curvature metric. And there exists a L infinity metric. And the singular set of that L infinity metric, sort of, if I state it in that generality, is at least 8, but the construction will actually give arbitrarily high codimension. And in fact, in sort of many cases, the codimension will just be equal to the dimension. So the original examples where all this comes from, they're all point singularities. But you have positive scalar curvature on the complement. And maybe let me add this as an additional statement here. Sort of moreover, we can assume that M is not homeomorphic to a PSE manifold. So to a manifold which admits a positive scalar curvature metric. So in that sense, these examples, they go beyond the sort of straightforward construction on the exotic sphere. They are not going to be that explicit, but they, in that sense, go beyond that because they are sort of, even if we are allowed to change the smooth structure, we run into the same issue. And so yeah, these are in particular more counterexamples to the obstruction part of this conjecture. Okay, so how do we obtain those? So they are obtained by chaining together the following ingredients. So the first is what I would call or what many people would call a pi-pi principle for a positive scalar curvature. And this in particular implies the following statement, that if you have a one-connected spin manifold, then you can delete a disk and you will obtain a positive scalar curvature metric on the complement, which is colored on near the boundary. So maybe let's draw a picture what this means. So let's maybe say this is our manifold M. And maybe here is the part where I deleted the disk. And then I have a color. So here, this would be Sn minus 1 times the interval. And the metric can be written as a color, meaning some metric on the sphere, which I call H, plus tt squared. And then maybe here, I'm just going to draw in the part that we deleted. This would be the disk part that we deleted. And so this is constructed using the essentially classical methods from positive scalar curvature surgery theory. And sort of what matters is that, in a sense, if you consider this to be a cobordism from the sphere here to, let's say, another sphere, if you delete another disk, then it's known that you sort of get from this sphere to this sphere by performing a number of surgeries, and you have to make sure that the codimension of those surgeries is at least 3 in order to be able to construct an interesting positive scalar curvature metric starting from one side going to the other. And this can be translated into a homotopy theoretic condition. And what in the end matters is that the fundamental group of that manifold here is the same as the fundamental group of the boundary. Or in other words, that the inclusion of the boundary is an isomorphism on the fundamental group, then you can obtain such a colored PSC metric. And here, in a sense, the situation is quite simple because we started with something one connected. We deleted a disk. The boundary is a sphere. It's also simply connected. So everything is trivial. And
but Rudi, do you need this condition?
say again,
you said you have a spin manifold.
Yeah, the spin condition is actually not necessary. You're right. But it's sort of for the examples, they sort of have to be spin manifolds for any case. So
yeah, sure.
And the argument is a little bit simpler if you have spin, because sort of what you want is that the inclusion is not just an isomorphism on pi1. Sort of technically, what you want is that it's two connected, so you have to perhaps kill pi2s, and that's easier if you have a spin structure.
Sure. Yeah. Yeah.
And then you reverse those surgeries and goes back. So yeah, one can say a little bit more about that, but that's so you're right. So spin is not needed here. So the statement is also true about spin, but there is sort of for us not going to be that useful. And now if we have that, what we're going to do is we're going to glue in a cone. So we start. So we have. We just take this and copy this. Oops. Get rid of this. And now then the idea is we're going to take that metric, and then in a sense what we want is we're going to make a cone here. So we're going to write down, let's say, this will just, so the interesting variable is t, and this will sort of go to 0 at some point r, and there will be some other constants here. And of course, we have to choose those appropriately in order to keep the scalar curvature positive. But the idea, in a sense, is that if we sort of go slowly enough, then since the scalar curvature of this metric H, so the whole metric G tilde has positive scalar curvature. So in particular, this metric H, which is on the sphere, also has to be positive, and it's going to be bounded below by some positive constant. And then we can achieve what we want here just by being slow enough here in this coning process. And then we can also try to interpolate this here in the middle a little bit to the color, to the straight cylinder, and we'll together get a positive scalar curvature metric with a conical singularity. And this is in particular an L infinity metric on M itself when we sort of pretend that this conical part here lives on the disk that we had removed. And it has positive scalar curvature on the complement. Okay, so that's the sort of a simple construction. Once we have a color, we can just cone it off. And then once we have this, we need examples where we can apply this idea. And here comes in the fact that spin obstructions, they actually give us simply connected manifolds without positive scalar curvature. And simply connected manifolds in high dimensions without positive scalar curvature, they necessarily have to be spin, and they are only spin obstructions. And they exist in dimensions which are 0, 1, 2, or 4 modulo 8, starting in dimension 4. This is where you have one connected manifold without positive scalar curvature. The examples, the standard examples, this would be in dimension 4, the K3 surface, which has a non-trivial A hat genus and therefore not positive scalar curvature by the spin obstruction. And then if you want to be simple, you can just take products of those, and you will get examples of this kind in all dimensions which are divisible by 4. And in dimensions 1 and 2 modulo 8, there you are in this realm where it's a bit more subtle, where we come back to these sort of smooth structure problems. There, typical examples would be certain exotic spheres, which also have a non-trivial alpha invariant in CMO2. So it's also an index invariant. And now, once you have these examples, you can just do the construction from 1 and 2. So you remove a disk, and then you find a colored PSC metric on the removed manifold, and you glue in a cone, and you get a counterexample to the obstruction part with the singular set, just this cone part. And this works in any dimension at least 8. And let's say any dimension at least 8, because in principle you had a 4-dimensional example here, but you can only sort of start applying the first step in dimension 6. So the first case where you can really apply this is the dimension 8. And it only works in these dimension parities a priori, but you can find other examples just by taking products with the torus of some dimension. That this sort of fills in the other potential dimension parities, although you will not get point singularities there. So once you have a sort of point singularity, you take a product with S1, then you have a manifold of 1 dimension higher, where the singularity is a subset, where it's submanifold of type S1. But it still sort of fits into the conjecture and gives counterexamples. And also, this is something, the part that I mentioned before already. Of course, if you work with these exotic sphere counterexamples, then you're again in this realm where it sort of depends on the smooth structure. But if you work with these examples here, so for instance, you take some products of K3 surfaces and some product of the torus, where here you take at least 2, then you will get a counterexample where the fact that this manifold does not admit positive scalar curvature is independent of the smooth structure. This is essentially because the A hat genus, unlike this alpha invariant, the A hat genus is actually a homeomorphism invariant. So it does not depend on the choice of the smooth structure. All right. So this is the sort of more general construction, which gives more counterexamples, and in particular counterexamples which are more robust in the sense that you cannot fix the problem by changing the smooth structure. And here there would also be another point where I would now move into a different direction, and there could be possibility for questions. Any
question? I apologize for my interference, because I have to run to my office because a horrible noise was there, and I was talking under this noise. So this is absolutely beautiful result, but I missed your statement of non-existence because I was running to my office at this moment. So what was a result of kind of when singularity is kind of smoothable?
Non-existence,
I
you
missed
mean?
probably 15 minutes of your talk because I was going to my office at this moment. As I said, at my apartment, at some moments with horrible noise. When I talked to you, I was really crazy with this noise. So I apologize again for my interference because it's a very beautiful picture. Yeah, you described here, but what was prior to that? So what I missed?
I mean, I think
Yeah,
here we
before
have
that.
before that. So before that, we had the essentially what I explained is that these sort of examples, which are now this general construction, I just gave a specific example, like a specific case of that, which is the exotic sphere, where you can, on the one hand, you have the disadvantage that the counterexample is in a sense not so strong because it depends on the smooth structure, and you're absolutely right that somehow the metric doesn't intrinsically see how you close up. But on the other hand, it's a very explicit construction.
Very good. No, I'm sorry. This actually answers all my questions. Yeah, I'm sorry. Yeah, I was completely was on the wrong line. Yeah. Yeah,
no problem.
Very nice.
It's very good to discuss it. I mean,
yeah.
Any further remarks or questions on the?
Now, may I ask the following? Would be true given any manifold of dimension, whichever, and you throw away some piecewise smooth set, such that the complement contracts to something of codimension at least 3, right? Then you can make this metric. Is it true? This is general conjecture. Any set can be realized as singularity insofar as the complement contracts to something of higher codimension. So the complement admits symmetrical positive curvature with convex boundary.
Yeah, I think a convex boundary, I'm not sure if that's enough. But I mean, if you have right, I mean, I think that coning construction here that sort of needs a bit that you actually need to have a collar, right? Otherwise,
yeah, it needs slightly. I agree. It needs slightly more. I agree, but still, I think something like that may be true, maybe in slightly higher dimensions.
But don't you have this collar when it retracts to a codimension 3 submanifold?
That might be the case, but I think you need a bit more than a collar because now you want to sort of to cone, but somehow you don't want to cone the whole thing to a point.
Right.
You want to cone to a submanifold on a singular set.
Exactly.
Right?
Yeah. Exactly. Slightly more than a cone, but I think you can again using kind of surgery type geometric kind of surgery and separate, spread this kind of in the right way, the boundary convex, keeping the rearrange kind of this handle structure. Handle structure one thing and then go to handle structure and other things. Well, of course,
but what kind of obstruction? What kind of obstruction do you have in mind then?
No obstruction given any manifold of sufficiently high dimension, and there is some manifold or even piecewise smooth object such as a complement has codimension at least 3. Then this manifold has this kind of metric, positive scalar curvature, all these conditions, and singularity along the set. That's natural conjecture, right? In the spirit what was explained.
I think that there might be a conjecture like that. I think it's not. I think given the surgery tools we have, it's not obvious how to do it. I think, but it's there is a conjecture, I think, along these lines that you might.
Yeah. No, but this is very nice. Exactly what the voice, what you say. Yeah, that suggests. Yeah. But do you have still results that under certain conditions you can extend it in dimension 4 and 5 or something?
I agree. I think, yeah, I mean, as I mentioned at the beginning, that there are these results on, enlargeable manifolds if you remove points and things like that, then
it's okay. Yeah.
Then we know the obstruction parts are okay.
Right.
And I think extension is something which I think is even there not known and obvious. I think that's would still be an open conjecture in a sense. And it's also, I mean, it cannot be true in a naive sense because of this. I mean, even if you take a diffeomorphism isotopic to the identity, you can sort of you make a local coordinate problem somehow that you can always do. So you always have to define it in a way that you exclude that case.
Okay, good. No. So it's exactly, I guess, it answers all my questions. Yeah, thank you. Yes.
Okay, so there would be sort of one more section. I don't know how, I think time-wise, which I can probably go through.
Time-wise,
So how long is
fine.
how long is the
Time-wise fine.
section?
The 1 hour talk with 3 breaks. So
Okay, so I mean, it's probably not. It's
you
not
get
long.
to
It's
talk for 60 minutes.
All right. Maybe then I'll just go on. It's not gonna be. I'm not gonna take too long anyway. So it's. Hope nobody minds. So I think the last part that I want to sort of mention is that now, in a sense, a question is sort of this approach is in a sense very, very global and make global topological constructions, and at the same time also these positive results. I mean, I didn't talk too much about the proof of those, but they are also in a sense of a global nature that you use some sort of global topological abstraction to the existence of a complete metric with positive scalar curvature on the complement of the singular set and things like this. This is what enters. And another possible question, like another possible approach to these sort of singular metrics is, okay, maybe we want to actually not sort of talk about the global topology, but we want to see to what extent a singular metric can be approximated by by smooth metrics while keeping a lower scalar curvature bound. And that this would be one approach of actually proving conjectures like that you start with a singular metric, then you approximate, you still get positive scalar curvature. So you can conclude that the original singular object cannot exist because the smooth object doesn't exist. And that there are sort of many people have been working on this, in particular on the sort of geometric flow, on the Ricci flow side. And I'm just going to mention sort of one result which sort of fits this idea, which is the recent preprint by Paula Burkhardt-Grimm, where she looks at again at L infinity metrics on Rn, and there is, however, a strong condition, which turns out to be important, namely that the metric in the L infinity topology, and here the L infinity is again with respect to the Euclidean background now, so you just work on Rn, is close to that. So it's L infinity close to the Euclidean metric. And the statement is that you start with such an L infinity metric, which is now smooth outside a singular set. And the condition is that it has finite n minus alpha dimensional Minkowski content, where alpha is greater than 2. So without saying too much about this, this is just in line of this condition in Chain's conjecture that the singular set should have codimension strictly greater than 2. And the scalar curvature should be non-negative on the complement. And then the statement is that there exists a smooth approximation. So there exists approximation of by metrics which are smooth on Rn. So a whole family of those which still have non-negative scalar curvature and which outside of the singular set in the sort of local C infinity topology converge to the given metric. And this so this is proved using essentially applying Ricci de Turk flow with sort of the Euclidean background and proving that flow, well, first of all, exists and has the properties that we have here. And now this sort of this is stated on Rn, but of course, sort of it's natural and conceivable, and there are also results by other people that this sort of works on a given manifold as well. Yeah, and then it means in particular if you have metrics in a sense of that nature, you will probably sort of, which satisfy a condition like this, you will get a potential way of attacking this conjecture under this stronger additional assumption. But since we have this counterexample, we already know that somehow such an idea cannot work like in full generality for any L infinity metric. And so in particular, if we, let's say, we want to drop this condition, say, and the question is, in a sense, how much of these constructions that we did before actually gives us, in a sense, quote unquote, local examples on Rn, which show that sort of this behavior doesn't exist in general. And in fact, that can be made to work. And maybe let's briefly recall the construction that I did sort of in the previous part. So, but I'm going to emphasize a slightly different aspect of this. So, in particular, from these sort of surgery constructions together with the index obstructions to positive scalar curvature, we got closed manifolds which without positive scalar curvature. So these were the simply connected examples where there exists a colored PSC metric once we remove a disk. And in particular, we can write here there's the boundary then the metric as some metric on the sphere, on the boundary sphere. So maybe let's do the picture again. So we had our M where we removed the disk, and then here we had the boundary sphere, and we had this metric here given on the boundary. And in a sense, this boundary metric is interesting. So it's topologically interesting in a sense that it does not extend to a colored PSC metric on the disk. So now it extends to a colored PSC metric on this part, but it cannot extend to a colored PSC metric on the disk. Because if it did, then in a sense you can just glue it together and you would get a PSC metric on the original manifold M, but we know that this was constructed in such a way that it doesn't have such a metric. So this is a topologically non-trivial PSC metric on the sphere, and they are in a sense like one of the sources of what's happening here. And now if we take that and if we essentially take a cone over that sphere to get a metric on Rn minus the point, this actually gives examples where sort of this sort of approximation cannot be possible. So this sort of is stated as our second main theorem here, which states that for like those dimensions where we have simply connected manifolds without PSC, there exists L infinity metrics on Rn satisfying a bunch of conditions. First of all, they are uniformly by Lipschitz to the standard Euclidean metric. So you can just bound them below and above up to some constant by the Euclidean metric. And they are smooth outside the origin, and the scalar curvature is positive. And it's actually, you can see it's bounded below by a constant times 1 over r squared. Yeah, so the scalar curvature actually sort of blows up at the singularity in the origin, but it's positive, and it's actually at the singular part is actually extremely positive, and it goes to infinity. But it does not exist any family of smooth metrics on Rn such that they have non-negative scalar curvature and they approximate the given metric in the local C infinity topology outside the origin. You could also just take C2 here. This would be enough. And what's the proof idea here? So the proof idea here is, in a sense, very similar to the other counterexample. Now you just really take a global cone over this metric H, and you sort of adjust it with a constant appropriately, such that the scalar curvature remains positive. This you can do, and now if you assume that there exists an approximation, if you can assume, if you have a smooth approximation of non-negative scalar curvature, then in particular, sort of, let's say you have your singularity here at the origin, and here you have the sphere, and you have your metric H living on the sphere here. And then if you sort of were able to approximate that cone smoothly, let's say, because it's sort of in the local infinity topology outside of the origin, it's actually uniformly in the neighborhood of the sphere, if you want, or in the neighborhood of any sphere. And then one can convince oneself that this would mean that the metric H, which sort of appears here at some slice, would actually have to be C infinity close to another PSC metric on the sphere, but which then extends to a PSC metric on the disk. Because sort of these approximations, they extend smoothly to the whole disk and have non-negative scalar curvature. And then, okay, so you can bump it up a little bit to make it positive also. And then this would give you a metric which is close to H and extends smoothly to the disk. But then if you have this, let's call this metric G tilde, this sort of thing that extends this metric which is close. But then you can isotope that metric which is close to H to H itself and fill that in with a positive scalar curvature metric here as well. And you would get a positive scalar curvature metric on the disk, which fills in the given metric H of a color, but sort of this was precisely what is not allowed to exist for topological reasons, so you get a contradiction at this point. And this is how you see that these sort of global examples that you constructed here, they sort of immediately also give sort of local phenomena. And maybe as sort of a bunch of final remarks on, especially on regularity properties. So far I only talked about L infinity metrics, and this is sort of very wild, but the examples that we construct, they are actually, in a sense, they have a certain Sobolev regularity, and the Sobolev regularity, the way I see it, or the way it turns out, if you compare it with other results in the literature, they are, in a sense, at the precise threshold where sort of approximation results like fail to work. So these sort of types of cones, they are, which one can verify, they lie in particular in the Sobolev space W2, comma P over 2, and that is for any P strictly below N. So they sort of, in terms of Sobolev regularity, they lie just below W2, comma N over 2. And so this is actually true for all the examples that I've shown you. When you construct them, these kind of cones, they have this regularity. And this in particular means that so far I've only talked about like the scalar curvature outside the singular set. This is maybe like from a conceptual point of view, maybe that looks maybe not as the correct idea. So maybe you actually want to look at the scalar curvature in a distributional sense or in a weak sense. And this actually means that the scalar curvature is globally defined in the weak sense, and it is an LP over 2 function for any P strictly below N. And the sort of final remark is that the rigid-Turk flow ideas, so there are these results by Paula that I mentioned, where you have this global closeness to the Euclidean metric, but there are also other types of results, in particular due to Lam and Simon and Chu and Lee, where you have approximation results if you lie in the Sobolev space W1N. And okay, so these examples here, they lie just below that. Yeah, they lie in W1P for any P strictly less than N. So in a sense, these kind of examples, they also sort of give sort of the nice observation that these approximations results that we have, they appear to be to be sharp, because sort of if you go a little bit above in the regularity, you will be able to locally approximate with Ricci-de-Turk flow while keeping a non-negative scalar curvature bound. Okay, and maybe this is a good time to stop then. Thank you.
Thank you.
May I again ask a question? Huh?
Yeah.
I'm sorry, I'll ask you so many questions. So when you have, for example, isolated singularity, then you can measure kind of the singular point is potentially scalar curvature by looking at hypersurfaces around that and seeing the mean curvature. For example, if you have polycubical neighborhood, then the dihedral angle of them in a way can represent scalar curvature at this point, right? So my question is, by how much in your example you deviate from that, right? So what you show apparently in these examples, you cannot extend the scalar curvature because already angular-wise it's wrong, right? Right. So because when you have for isolated point, you can say what it means having positive scalar curvature at this singular point.
In terms of a cone angle or something like that, you mean?
Not cone. No, not cone. You consider these cubes around that and see what are these dihedral angles and what the best cube you can make. This tells you what is this scalar curvature, how negative it can be, right? And so if you can start,
I mean, I guess for that dihedral angle approach, you would still want to have a smooth metric in the interior, right? Or otherwise.
No. To have this, absurd. But by this angle, you determine what is happening on this point. So, for example, if this angle condition satisfied, then probably it's extendable this way or another. For example, this may be conjecture, right? So what geometric condition on this outside metric needed to be extendable? And one condition I suggest, probably not the best one, but the obvious one, if all cubes around this point have the right dihedral angle to satisfy this cubical inequality, which is, well, similar to having convex. Is question number one, right? This is, if it's a non-isolated, slightly not so clear. So you still want to know what a singular metric of positive scalar curvature, what is the right condition. And so just see L infinity, just as you show in this example, not correct. Exact question number one. Question number two is that, as we know, more or less everything which do for scalar curvature, positive scalar curvature, is counterpart for hypersurfaces with positive mean curvature. So what happens? What we can say about that? Just what you have hypersurface with positive mean curvature, with isolated singularities or whatever. What kind of singularities can be there? And because if you have convex hypersurface, we remove small codimension set, of course, nothing happens. Yeah. But if with scaling mean curvature, it must be a different story. Is it so?
I don't know off the top of my head, but it sounds an interesting question, yeah. So,
of course, you can double. As usual, you can double and apply to whatever we do for the double. But this, of course, there must be more direct approach to it. Because surgery is possible also, because the category of positive scalar curvature. And this kind of, I'm using because much more elementary matter, I just hypersurfaces in Euclidean space. And then it may have some relevance, of course, to minimum hypersurfaces also.
So you mean the singularity really is at the hypersurface, right? At the boundary.
Hypersurface is singularity, yeah. And it's but so what happened? I think there might be parallel discussion to everything you are talking to. Well, again, in all examples, they're parallel. So there are two questions. So just how to steal? You still may not lose the hope of defining singular spaces with positive scalar curvature, but you have to define this more carefully.
Yeah.
And second, the same to try it first for hypersurfaces with positive mean curvature, where we have more intuition, maybe geometrically. But this example of yours are very, very, very kind of convincing. Yeah, I think they just really tell you what you cannot ask. Yeah.
Yeah.
Rudi, one point. So in particular situations, for example, we have a sphere and we remove the antipodal points, we have a rigidity without the L infinity assumption, away from the antipodal points.
Right. Yeah.
But so the discussion that you carry out here seems to be sort of go in a slightly different direction, right? So we still do not know much about the problem when we drop the L infinity assumption in certain situations, like on spheres. Let's take a sphere and then we remove finitely many points, or we take the round sphere and remove just 2 points, but which are not antipodal. So
No,
then
I think it goes in a
question is-
different direction. Yeah, I think that's.
Yes. Okay.
I think, yeah,
And this is still open, right? Yeah.
Yeah. I mean, I think, yeah, if you have L infinity, then this is known, but then I guess this is sort of turns out to be a different and easier problem than if you don't have the.
Do you have, can you speculate here? Do you think that this is maybe then just wrong? Or, I mean,
I don't know. I mean, I think I don't have a good intuition
okay, yeah.
I mean, at least not, let's say, not from these examples. I think I think
But
that's.
you're right, Bernard. I think there must be link between the two. Yeah. Maybe you have to mediate and find something in between. It's maybe the spectrum of
Exactly, yes. That's what I mean here.
results and conjectures.
Yeah.
Absolutely. Yeah. It would be extremely interesting to have encompassing both results, both problems. There might be quite profound relationship here.